Okay, we've been spending the last couple sessions and just the remaining time this quarter talking about output analysis. So far, we've looked at terminating analysis and found an approach that is as reasonable as one could get on that. Namely, for terminating, we run the model once, and then we reset everything except not our random number generators, and we run it again to get an independent replication. So the whole issue is that and we're going to see that it kind of up close and personal here, is that in order to have valid statistical analysis, and we've been focusing on finding a confidence interval for a measure such as delay in queue, we need to have an estimate of the variance. And when data are correlated, we cannot get a good estimate of the variance. That's just kind of something we're stuck with. That is, the normal estimate of the variance is biased when the data are correlated. And for positively correlated data, which are typical of simulations, I mean, it's not all data, even in simulations, are positively correlated. It's possible to have a negatively correlated data, but most are positively correlated, and we're going to see that, if not today, tomorrow. In that case, the usual estimate of the variance is biased low, which means that it severely underestimates what the true variance is. And that's a problem, because that means that our confidence interval is going to be much smaller than it normally is. In other words, we may think we have a 95% confidence interval, but it really could be like a 40% confidence interval, because our estimate of the variance is much smaller than it has any right to be. So for the terminating case, we overcome that by doing multiple independent replications. And so with each replication, if you remember, let's say we're interested in expected average delay in queue. And again, for that, each customer has a different delay in queue, and we're going to see that also. And we can still estimate the expected average delay in queue over all the customers in that particular replication by doing multiple independent replications. So the independent replications, and if we do those replications with the identical initial conditions, then we have independent, identically distributed data. And then we can form a legitimate confidence interval with the usual caveats about central limit theorem and normality and all that other kind of stuff. Now, if we're interested in steady state, though, that's a different matter. There are basically kind of several issues with steady state. Okay, the first is reaching steady state in the first place. And for that, we will have to kind of deal with that. And then even once we reach steady state, we are still confronted with the issue of the data being correlated. And so our solution to that is going to be to truncate, that is to warm up. And that's an example of, well, it's like you go to the doctor and say, what's the matter? It says, it hurts when I go like this. I say, well, don't go like that. So the problem, as we will see, is something called initialization bias, meaning that the observations in the early stages of the simulation are typically very biased, and they can be very badly biased. We're going to see an example of that. And so the solution is going to be something called replication and deletion. Okay, so let's hammer on these issues with steady state. So the first is that the initial conditions are not typical of steady state. In other words, in our queuing model, and that's going to be our canonical example, we start off with nobody in the system. And in steady state, it may fluctuate with a lot of customers in the system. So those initial conditions are not typical. And so when we start up the simulation, we're going to get values that may be wildly different from the ones that we're going to get in steady state. And again, we're going to see an example of that. So that terminating analysis that we were doing, in which the initial observations had a big role to play. In other words, if we open our store in the morning when we have no customers, and then we close the store, hopefully letting all the customers out eventually in the late afternoon, then that system may not have even come close to reaching steady state. And we will never see that because we shut the store down. But if we run our model long enough, we may see something very different. In some models that I'm working with the naval support system, they're very much interested in some long run models. And so for those simulations, we have to run it to steady state. So the other thing, the initial observations are typically biased with respect to steady state measures. And in steady state, the observations are still autocorrelated. So here's a way to think of this. So this line here, this is the true. Notice the fact that this is a very smooth curve indicates that this is not simulated data. This is like, this would be the true but unknown amount. So let's say that this is the measure we're interested in is the average delay in queue. So when we start off, remember that those first few guys are going to have 0 delays in queue. They're going to be way down here. And then as customers start coming into the system and getting processed, and this is the true but unknown average delay in the queue. Say for like this customer, this is the true but unknown expected delay in the queue for say the 10th customer. This line, the red line, that is the true, again, but unknown steady state expected delay in queue. So in other words, if we run our model long enough and say, what is the average, what is the expected value of a customer time in the queue? This is the value that we would get if we run it long enough. But this is how the simulation, this is the actual value. So if I only run my simulation to here, see the difference between the blue line, which is what I'm getting, and the red line, which is what I'm after. And that difference is bias. And here's the thing, as we saw with the terminating case, and as you hopefully remember from your statistics classes, if you want a tighter confidence interval, if you want to have a more accurate estimate of, say, your mean, you take more and more observations. In this case, if I take more and more replications, I get a better and better estimate of the wrong thing. So what I really want to do, is find some place here and throw out all these observations. I want to discard these early observations. Why? Because they're biased. It hurts when I go like this. These values are actually pulling my estimates away from what their values are. And the more observations I take, the more these are going to be pulling things down. So just to kind of illustrate this, one of the things I've pushed to GitLab is you should see a bunch of stuff. There's a class there called Initialization Bias Demo. Okay, and that's taking basically let's see, what did I tell? Oh yeah, this was our entity server model from way back. Again, we're going back to uniforms and gammas. I just wanted to reuse that. I'm looking at delay in queue. So this is what this is going to do is illustrate this. And in order to really demonstrate it, I kind of bumped up the number of replications by a whole bunch. But just to kind of show you how that does, that takes a few minutes to run. So I'm going to look at 10,000 delays in queue. And what this is going to do is for each customer, it's going to estimate the average delay in queue for each customer. In this case, for 10,000 customers, I'm going to run just for 30 replications at first, just to kind of show you what that is. That just runs in a couple seconds. And to see what that looks like, let's open. Okay, this is the file I just generated. Okay, so this is the delays in queue. These are the average delays in queue, in this case, over 30 replications. Notice that the first two are 0. Why? Because there were 2 servers. And so the first 2 customers are always going to get 0 delay in queue regardless. So, but let's take a look at what this is actually looking like. So we can just easily, this is one of the things Excel is really good at. Okay, so this is with 30 replications. Again, we're starting at 0. It kind of climbs up and wanders around here for a little bit. But notice it's still kind of jagged. Okay, we only did 30 replications. So that's really not all that many. That's why it'll take a few minutes so I can kind of talk at you a little more. When I did 5,000 replications, again, it runs in about 3 minutes. We can get a better idea of what again, a slightly better curve that will show us what the delays in the queue are. And again, this is over 5,000 replications, so this should be fairly tight. And we're going to look at 10,000 delays. Okay, now how did I do that? Well, okay, I have an output file. I did a little dance to make sure that I had the directory there. There are a couple of new classes. There's one called the property data logger. That's the one that actually stores the raw data. And then I created a list of sample statistics, which I populated with simple stats tallies. And so what I did is over all the replications, again, I reset the simulation. I reset my raw data logger. That's the kind of like the inner one. And then after each one, I actually got the data, the raw data. So here, this would have 10,000 of these guys. And for each one of those, I got the simple stats tally for that particular one, added a new observation from the ith raw one. And then for my property data logger, that's the one it writes. What the property data logger, it's an extension of a CSV data logger. It basically writes a CSV file, and it can handle multiple states as well. We'll see an example of that when we look at the autocorrelation issue. But this thing is still running. I think Zoom is kind of consuming too much CPU for this. But at some point, it will actually write the values. And when that happens, we will see, hopefully, a curve that looks a little bit more like this, again, without the red line. Because keep in mind, we don't know any of these values. This is all sort of a hypothetical. And we're still running here. So just, I can maybe point out some of these other things. So the raw data logger, okay, it's just a property change listener. And what it does is it has a list of doubles that it's going to keep the data in. And like the simples, like the stats objects, it has just one property that's going to keep track of. And what it does is, in responding to the property change events, here's how I say, well, if you're not my if you're my property, I'll listen to you. Otherwise, I'm going to ignore you. And if somehow you're a number, I'm going to get that double value. And then this is where, if you remember, for delay in queue, the very first values were not a number, and I want to ignore those. So if you're not a number, I'm just not going to, I'm going to ignore you. Okay, so it took almost more than 3.5 minutes to do that. All right, so let's see what that one looks like. Where did it go? Do I need to close this one? Let's try that again. All right. So let's see what that one looks like. And as you can see, okay, with that many replications, you know, it's still a little bit wiggly, but this here we get a better sense. That looks a little bit more like this one. Okay, why? Because the number of replications kind of smoothed things out. They got the estimates to be much tighter. The one that was all jagged, we only had a handful of observation. We had like 30 replications. That's still a quote, a lot, but it still was not terribly tight on this. Here, despite these little wiggles, you can really see that it should be absolutely clear that our steady state mean is actually closer to around 35 or so, and not these values here. Okay, so now what about autocorrelation? That's sort of the other. So that's the initialization bias demo. Okay, so here's there's another class called output raw data. So for this, instead of doing multiple replications, again, I'm taking the same one, and now I'm just doing 100,000 n completions. But I'm also looking at both delay in queue and time in system. I don't know, why did I, just to illustrate this CSV property data logger. It's going to write a CSV file, and this one goes by fairly quickly. So again, we're taking our entity server, using the parameters that we were using there, and we're just going to run it for 100,000 completions. And then we're going to use that to, we're going to have to pull it into jump and estimate our, okay, so there it wrote a CSV file called raw data. And we need to, let's open up jump and import that. So actually here's the data. And as we see, it was the delay in queue and time in system. It had both. Let's do next, and then let's import that. Now, so this is to show the autocorrelation. And in jump, at least the way I could find it, was they have something called specialized modeling time series. So if we do that and we select our, we'll select, well, no, let's just do delay in queue just for. Okay, yeah, remember, this is just one replication. And notice that it's sort of claiming that the mean is around 30. And we just saw that the mean is probably closer to 35. So right off the bat, this one replication is not necessarily indicative. But the key thing here to look at are the autocorrelation right here. So what this is the lag. So this says that the autocorrelation between something and itself is always 1. Okay, the lag 1 autocorrelation, that's the correlation between the delay in queue for one customer and the next customer. In other words, the correlation between the delay in queue for one customer and the guy next to him is 0.9991, according to this estimate. Really high. And in fact, the correlation between the two guys behind him, in fact, if you look at the lag here is 20, like down to 25, even at 25 customers behind, the correlation is 0.98. That's really, really big. That's really big. And so correlation is kind of the opposite of independence. What this is clearly showing is that there is a high positive correlation between successive delays in the queue of the different customers. And that's something we have to deal with. And that was something that was, that we kind of talked about, or at least I talked about, and why we need multiple replications and why we can't deal with the individual observations. And we saw that in the terminating case. That's why we can't just do one long run like this and estimate the delay in the queue. For one thing, in the terminating case, we were dealing with, say, a facility that opened in the morning, closed in the afternoon. They were only open for like 10 hours or whatever. And so it never reached steady state. It never had a chance. So, in that case, that was always way down here. In other words, that facility that was closing at around this time, whenever this was. So let's say if the facility closed around here, the values that we were getting were not indicative of what would happen if we ran this model out to infinity or for a very, very long time. Okay, so all of this to say that the problems or the issues that we have to deal with when we want the steady state, value, which is what we want here, we want to find what this guy is. And we don't know what it is. All we have is we just have our model, and the way our model works is it's going to run like this. And as I hope you saw, that this isn't just sort of even though this graph is of the theoretical value, what we saw was that that's in fact the way that delays in queue look if we kind of take enough samples and take a look at that. Okay, so what are we to do? Now, so to deal with initialization bias, we want to truncate. And truncation means the other term that you'll sometimes see is to warm up. Warm up. In other words, we need to kind of warm our system up until it's kind of running smoothly. It's like when you start your car in the morning and it's stone cold, it's not going to be running exactly the same as once it reaches its running temperature. Okay, so the initial bias observation of bias, so it hurts when we go like that, don't go like that. So for tally data, so let's say that we want to truncate after t observations. And what that means is basically the mean that we want is we will take n observations after the truncation point and take the average of those. And that will be one. That's going to be one observation. And then we're going to try to replicate that. For time varying data, we do just have to do something similar. For there, we will typically say, we'll choose a time, t for time. And now there'll be a warm-up time of t and a time in steady state of s. In other words, we're going to, just to kind of, if this is t, we're going to run it for s time units if we're doing time varying data. So the truncation point is either the number of observations for tallies or a time for the time varying data, or we can also truncate at a certain time, and just the you don't have to worry so much about the particulars of the notation. But in other words, even if we have a tally, it turns out sometimes we want to say, instead of running it for a certain number of observations, we're going to run it for a certain amount of time, and then collect observations for a certain amount of time after that. Okay, so the notation just gets a little bit tricky here. So if the times when, again, think of the delays in the queue. When do delays in queue happen? They happen at the start service event. When does that happen? Well, we don't really know. That's what these little t sub i's are. So if we're going to run for a certain number of observations after the truncation point, that's what this sort of n of t is, then these are the times when they occur. And again, we just basically take the average of them. That's just sort of the normal thing. So again, so for steady state, unlike the terminating case, the measure is a single value. But if we are in steady state, the data actually do wind up being identically distributed. That is, they at least have the same mean. I don't know why R is in there. Okay, so they at least have the same mean, but they're still correlated. So as I was claiming, the usual estimate of the variance is biased. So in order to form our confidence interval, we still need to get to IID. So we actually have the second I. If we in fact have reached steady state, they actually are identically distributed, but they are not independent. They are correlated still. And that's what we saw here. Again, let's kind of go back. Here's what we saw. These were the observations that were just I generated these in front of you. Or I'm sorry, we want these guys. Again, this was one replication in front of you. And we see a tremendous, huge correlation. In fact, that correlation goes way out. Oops, we don't want to forecast. We just want to just a time series. The lags are 25. Even if we go out to 200. Oops, we need one of these guys. Okay, so even if we go out to 200, we're still 0.87. Okay, what does that say? That what that means is the correlation between any customer and the customer that's, say, 200 in back of them is still 0.87. That's huge. In other words, what tends to happen, and we can see a little bit of that kind of right here. What happened here for this particular replication was all of a sudden there was this, just by chance you get this, there was just this influx of customers that overwhelmed the system. So for this period of time, the delays in queue just got out of hand. And then what happened was that it was finally able to process them and get back to sort of a more, quote, normal place. But these kinds of things happen. So the point is that this autocorrelation it's a real thing. It's a thing that really gets in the way of our statistical analysis, which leads to our method, which I'm going to describe now and demonstrate tomorrow. There actually are a number of different ways that this has been approached. The most straightforward and brute force way is it's called replication deletion, or deletion replication. So the idea is that we will do one replication. So one replication, we're going to truncate data at the truncation point, and that's going to be the deletion. And then we're going to continue to sample in steady state. In principle, all we need is one observation in steady state, and then that would be enough. But in practice, what happens is we still want to take a bunch of them and take the average of that. Because again, once we're in steady state, all the observations have the same mean, but they're correlated. When we're in a situation where the variance is very high, we want to kind of bring that variance down. And so one way is to just keep sampling in steady state for a while, but that's still just going to give us one observation. So we take that aggregate measure in steady state. So for example, the mean becomes one observation. And then we lather, rinse, and repeat that. And if we repeat that independently, see, now we're back to IID. So if I do that once, that is, I warm the system up, I discard all the data for that, then I keep running, that gives me one mean. Then I do the whole thing all over again. And that will, if I follow exactly the same procedure, and I've reset all of my, well, actually resetting the state variables is actually not as crucial here, because steady state does not depend on initial conditions. But I still, just to be, careful, I still reset it because I want to follow exactly the same procedure, but with independent random variables. And then I get an independent replication of this aggregate measure of the mean. And then I repeat that independently. And then again, now I'm back to IID. Now each of these are going to give me independent, identically distributed observations of the steady state mean that I want. And the only issue now has to do with whether I've reached steady state or not. And that that's actually a very interesting and in many ways kind of an open question to have a strict formal way of doing that, to say, okay, follow this and that's it. In practice, all we have is kind of is to kind of look at something like this and say, well, it looks like we hit steady state maybe around here or so. So we'll throw away all these guys and then just use these ones. There are, if you read simulation books that talk about this. There are a number of fancy methods. And my problem with the fancy methods is they have all this math and all this sort of stuff, but in the end, it comes back to just looking at eyeballing it. So that there is one formal method that requires about a quarter or two worth of extra math in order to get. And that's actually a really cool one. So we're not going to talk about that. Basically, the idea is that you do something like this. You just kind of, you run the bejesus out of it and you say, well, okay, here, it looks to be around here. So I'll choose a truncation point around this many observations. So tomorrow we'll see an example of this in action. But for today,